Hello everyone, I am Mayukh Mazumdar, Assistant Professor in the Department of Physics, Salesian College Autonomous, Siliguri. Today I am here to discuss a very interesting problem on a very important topic named particle in an infinite potential well. So this topic is from both the modern physics as well as the quantum mechanics courses from our 4-year undergraduate program. So without further delay, let's delve into the problem. So this problem is from a previous year question from IIT JAM 2023, which was organized by IIT Guwahati. So the problem is like this: if the ground state energy of a particle in an infinite potential well of width L1 is equal to the energy of the second excited state in another infinite potential well of width L2, then the ratio L1 by L2 is equal to, and the options are 1, 1 by 3, 1 by root 3 or 1 by 9. So before we begin the solution, let's briefly recapitulate the theoretical background. So we have a particle in a one-dimensional potential well. So you may ask that why have we specifically chosen one dimension? The answer is in the question. Only one information regarding the size of the potential well, that is its width, is given. So if we have a one-dimensional well which can be defined by the potential function Vx, which is 0 as long as you are within the well, and beyond the walls of the well it's infinite. So the particle is trapped inside the potential well. It's acting like a free particle within the walls of the well, and it's not allowed to go outside the well. If we use this potential function to solve the Schrodinger equation, we will be getting the solution. The wave functions will be like this. So the normalized wave functions would be like root over 2 by L sine n pi x by L. What is this n? I will come in a while. And the corresponding energy eigenvalues can be written like En equals pi square h cross square by 2m L square into n square. Now this n, you can call it the quantum number, and it can assume only values which are natural numbers 1, 2, 3, 4 and so on. Now I will give a list of n values and the corresponding energy eigenvalues. So for n equal to 1, we will have the energy eigenvalue equal to pi square h cross square by 2m L square, and this is the lowest possible energy that the particle can possess while it is inside this well, and we will call it as the energy of the ground state. The next highest value of n, which is 2, will give us the value 4 pi square h cross square by 2m L square, and this will correspond to the energy of the first excited state. So this is the first excited state energy. The next value of n, I can choose 3, and if I put this value in the formula for the energy eigenvalue, I will be getting 9 pi square h cross square by 2m L square, and this will be our energy corresponding to the second excited state. So similarly, I can go on listing down further n values and corresponding energy eigenvalues, but that is not necessary because in this question we need only the ground state energy and the second excited state energies. So we are good to go now. So I will just draw the potential wells. So for the first potential well, I can have a rough diagram where in the vertical axis I will be plotting the potential. Along the horizontal axis I will be plotting the dimension x, and between 0 and L1 I will have the potential well. So as you can see from this picture, the width of the potential well is L1, and the ground state energy for this case will be, I will write it as E1 pi square h cross square by 2m L1 square. We just now saw that this will be the expression for the ground state energy. Now we have another potential well of a different width, L2. I'll also draw it in the similar way, L2. So that's the width, as you can see in the diagram. For this one, I'll be designating the energy eigenvalues with E prime or E dash, and this is the second excited state. So the n value is 3, so I'll be writing it as E3 prime pi square h cross square by 2m. Keep in mind, now you have to put L2 square in place of L square, and 3 square will give you 9. So we have all the ingredients. Now getting back to the question, these two energies are equal, that is what they have said. So let's equate the two energy values, and once we write them, it turns out that except for few terms, most of the terms are common on both the sides of the equality, and we can cancel them out. Let's do it one by one. Great. Now we have a very simplified form of the equality. Now let's take the ratio of L1 and L2. First we have to take the ratio of L1 square by L2 square, that will be 1 upon 9. We're almost there. Now we want the ratio L1 by L2. So let's do one thing, let's take the square root. That would be the square root of 1 upon 9, and these are lengths, so the negative value of L is absurd, so we'll take only the positive root. So there you are. So the answer should be 1 upon 3. So congratulations, you have solved the problem from IIT JAM 2023. That's it from my side. Thank you for staying through the lecture.